Okay, hello. So this video is a video response to a really nice black pen, red pen video that I saw where they proved this limit. If the limit of f is L and the limit of g is m, then the limit of f times g is L times m. So of course this is like a fundamental part of limits. The product of the limit is the limit of the product. But actually the proof is quite technical and long. So if you just start jumping into the proof, like if you just jump into the proof and you start going with epsilons and deltas, it gets quite messy. And you can do it, and that was a really nice video where they did all the details and really showed like step by step what you do in the proof. But I wanted to make this video to show a sort of bigger picture way to look at it where you can still get the proof, but it's a little easier to see what's going on. And so before I do the proof, I'm going to do the non-proof. So here's the non-proof. What are we given? We are given that the limit of f of x equals L, and that's really saying f of x minus L is approximately 0 when x is approximately a. So this is what we're given, this limit. We're given that f of x minus L is approximately 0 when x is approximately a. And of course, when we go to prove it, this approximately 0 is going to say absolute value of this less than epsilon. And this approximately a is going to say x minus a is less than delta. But fundamentally, this is what this limit means. That's the first thing we're given. And then the other thing we're given is that g of x minus m is approximately 0 when x is approximately a. Like this is what these limits mean. So if you write down the epsilon-delta definition right away, you will get bamboozled by all these Greek symbols everywhere. It's really important, at least to me, the way I think about it, to remember what it is like as an idea. And this is the idea. F of x minus L is approximately 0, and g of x minus m is approximately 0. All right, that's what we're given. What do we want? Want to show? What do we want to show? Well, we want to show the limit of f times g. So we want to show f of x times g of x minus L times m is approximately 0 when x is approximately a. That's what we want to show. So this is what we're given, this is what we're going to show, and it's written in ideas, not in Greek letters. We're going to convert it to Greek letters once we get the idea. So how could we combine this and this to get that? To me, there's only like one, like you have f and L, you have g and m, and you want to combine them in some way to get f times g and L times m. So what could we possibly do? So idea, to combine them. What could we possibly do? Let's try multiplying. Multiplying. That's the first thing that comes into my head. So I'm going to take this first thing in brackets, f of x minus L. We know that's approximately 0. And we know the second thing is g of x minus m. That's approximately 0. So if we take the left-hand side of this guy and the left-hand side of this guy, and we multiply them together, what do we get? We get f of x times g of x, so I'm just expanding here, FOIL minus L times g of x minus m times f of x, and finally, plus L times m, right? So by multiplying, this thing is approximately 0, this thing is approximately 0. If you multiply them together, that should still be approximately 0. So we know this is approximately 0. 0 is approximately all this stuff. And on the other hand, it's equal to this nice expansion. And this nice expansion has an f and a g, which is what we want. It's got an L and an m, which is close to what we want. It's with a plus. We wanted a minus. So how can we do this? I think the secret is to look at this f and this g and figure out what are those close to. And so this whole thing is approximately f of x and g of x minus L times, here there's a g, and the limit of g is m. So this is approximately m, and this is an f, and f is also approximately L, and we have plus Lm, and so this is approximately f of x, g of x, minus Lm, because we have 2 copies of Lm over here, and we're adding on 1 more copy. So this is the core idea of the proof. We want to show that f times g minus L times m is approximately 0. How are we going to do it? We are going to take f minus L, we're going to take g minus m, which we know are approximately 0. We're going to multiply them together, and then we're going to have this algebraic expansion, and we're going to look at the individual parts. And because the individual parts are doing what we expect, like g is approximately m and f is approximately L, we can add them together to get what we want, which is that f times g minus L times m is approximately 0. So the right-hand side is what we want. What we want is approx 0 because the left-hand side, what we have, is a proxy. So that's like, this is the core idea of the proof. So of course this is a non-proof. This is just like hand-wavy thinking, but we are going to convert it into a proof. And when I convert it into a proof, I'm going to take all the technical stuff and I'm going to put them in lemmas. I'm going to try to make the proof of this result only have these big ideas, and I'm going to save any kind of like technical thing we need into a lemma. So for example, here I had that G was approximately M, and I replaced L times G with L times M. This is saying that if G is close to M, then L times G is close to L times M. That requires some proof. So this is going to be a lemma, whereas we're not going to prove it as part of the main result. We're going to prove it as a sub-result and just use it in the main proof. Same idea, we're going to need that when you, if you can add together things, then the adding together works, right? So here, suppose this thing is close to L times M. Is it true that this thing, if this thing is close to L times M and this thing is close to M times L, that you can add them together like this? Like, does that actually work? So we're going to have to prove that too, but that's also going to go in a lemma. So in my actual proof of the theorem, I'm going to take everything in my non-proof. Let's make the non-proof a little section, and I'm going to convert it into rigorous math, and I'm going to save all the technical results that really have the hardcore epsilon-delta stuff for lemmas. So here is finally, my actual proof of the thing. So I'm going to make a little proof environment, which in Elix you can go environment and hit proof. Where's proof these days? Proof! Okay, so here's the proof. And again, it's going to involve epsilon-delta. We're going to convert the stuff to epsilon-delta. So given any epsilon greater than 0, we want to show that the absolute value of f of x times g of x minus L times m is less than epsilon. This is the conversion of this result. This is what we want to show, right? F of x minus Lm is approximately 0. That means its absolute value is less than epsilon, and that's going to work for any epsilon greater than 0. When is that true? We want to show that there exists a delta greater than 0, so that whenever absolute value of x minus a is less than delta, that is this part, this holds. So I've written down the rigorous version of what we want to show. What I want to do is I want to use this main idea that we used. So we are going to rewrite as follows. And we're going to write f of x times g of x, f of x times g of x minus Lm. Our key inspiration is going to be these equations. So this thing was the thing that was approximately f of x times g of x minus Lm. And so I'm going to convert what I have, which is f of x times g of x, into this whole shebang. So I'm going to add on all these things and subtract them off. So I'm going to write like this. This thing, which is what we have, this is equal to what? So I'm going to make a little equation array like this. I'm going to add on and subtract this much. So I'm going to do absolute value of f of x, g of x, and then I'm going to do minus all that. Okay, don't forget the Lm. So far I've just subtracted off this stuff. Then I'm also going to subtract off the Lm, minus Lm. And now you got to add everything back on. So if you were going to do it properly, you would take all this stuff and add it on like that with a minus sign. So let's put it all in brackets. Minus sign. Why don't we do it like this? So let's do all the stuff plus and all the stuff minus. Okay. All right. I think this is a key moment in the proof because this seems like total craziness. If you just were reading the proof and you saw this, you'd be like, where did all this stuff come from? And the answer is it came from this idea. So I think the idea made perfectly good sense, and now we're using it here. And if you watch the other video, you'll see that there is also the same kind of idea of adding and subtracting something. So, if you know where it comes from, it makes perfect sense. If not, it seems crazy. But that's what it is. And okay, the whole point of doing this was to put this guy and this guy together, because this guy and this guy together is exactly the absolute value of f of x minus L, and then g of x minus m. That was all this stuff. Let's write everything else minus this stuff. So okay, I took all this stuff, I made that like this. We have everything else that's over here. And what is everything else that's over here? Let's simplify it a bit. copy paste, copy paste. Okay, we have a plus L times G. We have a plus M times F. We have a minus L times M, and we have another minus M L times M. And all of this stuff is inside an absolute value. Okay, and now is the moment to use the triangle inequality. And you saw this a lot if you saw the other video. The triangle inequality comes up all the time when you have these absolute values. In this case, we have this nice term, and we have L times G, but with a minus L times M, and we have M times F with a minus L times M. So what do we end up with? We have by triangle inequality. Let's try to make the triangle inequality actually work. Less than or equal to the first term, plus, and how am I going to combine all this stuff? I'm going to put L times G with one copy of the L times M, so minus L times M. Put that guy in its own little bracket. And then I'm going to add on everything else over here. Okay, so I've split this into three parts. F times G, F minus L times G minus M. That was the main head honcho that we were going for. And then we have these two other parts, L times G minus L times M, and M times F minus L times M. And if you remember, comparing to our original idea, that was exactly this idea, right? L times G and L times M, and M times F and M times L. That is exactly what we had before. So like, the main ideas we have are coming out in the math just naturally. I'm going to do a little bit more simplifying, and I'm just going to write that this is the absolute value of f of x minus L and the absolute value of g of x minus M. And then over here, I'm going to do plus L times the absolute value of g of x minus M plus M times the absolute value of f of x minus L. Okay, so I factored out an L from this guy, I factored an M from that guy, and this guy I factored as two parts. And now we are in great shape because we have four things, 1, 2, 3, 4, and all four of those things are things that are coming up in our given, right? We are given that f of x minus L is small. Well, it's going to be, arbitrarily small. G of x minus M is arbitrarily small. G of lowercase x minus m is arbitrarily small, and f of x minus L is arbitrarily small. So now we are going to be in a great shape to use what we are given to make it work. And again, there was a lot of this that was really well done in the black pen, red pen video. This is just another way of doing the same thing. But I like starting with this intuition, and you can see how it translated into the actual equations that we have. Okay, so here is our rewriting. So now I'm going to be choosing some epsilons and deltas to make these things small. And it looks like I have three terms. So let me try. I'm going to try to make each term less than epsilon divided by 3. And this part is going to remind you of the actual video. So we're going to try to make this, less than epsilon by 3. And we're going to do that for all three parts so that when you combine them, you get something that is less than epsilon. Okay, so let's try it. So how am I going to make, these two terms are easy. Let's do these ones first. Yeah, let's do these two first. So choose delta so small so that absolute value of g minus x minus m is less than epsilon divided by, if I just made it epsilon divided by 3, then when you multiplied it by L, then you would be in trouble. So I'm going to also put an absolute value of L on the bottom here, so that when you multiply it by L, you get something that is less than epsilon divided by 3. And this was in the video. If L equals 0, then you have a problem. So you can fix it by doing a little +1, and then arguing something like that to make sure that you're never dividing by 0. If L equals 0, then this thing is going to be 0 no matter what. So I kind of prefer doing cases. So I say if L, so I'm dealing with the terms term by term. Let's deal with the terms term by term. Deal with the three terms individually. And the first term that I'm going to deal with is this term, L times this. if L equals 0, this term is 0 and is definitely less than epsilon by 3. If L is non-zero, then we're going to do this. We're going to choose delta so small so that g of x minus m is less than epsilon over 3L. And now there's no dividing by 0, nothing like that. I guess this term is the middle term. Okay. So we want g of x minus m less than epsilon over 3L whenever absolute value of x minus a is less than delta. Okay. And I suppose this is the middle term. Let's call this the second term. The second term. So the second term. Let's do a little organizing here. Let's make this the second term, and the second term is this. And here's my argument for the second term. Oh boy. Okay, went a little right. Okay, here, this is my little argument for the second term, and let's call this delta. Let's call this delta 2. 2 because it's the second term. Delta 2. Whenever this stuff happens, delta 2. Okay, so just to make sure we're on the same page, epsilon was given to us all the way up here, and we chose delta 2, where as long as x is within delta 2 of a, absolute value of x minus a less than delta 2, then this middle term is going to be less than epsilon by 3. Okay, and that's handled. Second term. So the claim is this thing is going to be less than epsilon. Whoa, that's not what we want. Okay, epsilon. Try one more time. Epsilon divided by 3 whenever absolute value x minus a less than delta 2. Okay, so have delta 2 so that. And this really is a little lemma. This is a lemma. So this is a little sub-argument that gives us this result of finding the delta 2, which is positive, so that this works. And so this is the proof. This is really the proof of the second term lemma. So I'm dealing with the three terms as little lemmas. And this lemma is sort of equivalent to the property that if the limit of g is m, then the limit of L times g will be L times m. But here we're dealing with it more directly. And this works because, once again, since the limit as x goes to a of g of x equals m is given to us. Okay, that's the lemma for the second term. There's also going to be a lemma for the third term. And we're going to find delta 3 for the third term, so that m times the absolute value of f of x minus m is less than epsilon by 3. Let's make it fancy, epsilon divided by 3, whenever absolute value of x minus a is less than delta 3. Okay, and the proof, this is a nice thing about doing lemmas, is you can reuse the proof. So I could copy and paste it and modify, but I think actually an even more readable way is to say same exact, let's say an analogous argument as for the second term lemma. Okay, and we gotta fix the typos. This is f of x minus L. And that way you kind of like avoid doing the same thing twice. So I like that. You could copy and paste it and change all the m's to l's, all the g's to f's, and so on. So either way, it's totally fine. But I like it like that. Okay, so we've done the second term and the third term. And so the second term is going to be less than epsilon by 3. The third term is going to be less than epsilon by 3. And now we just have the first term, which is the actual hard term, or first term. But I hope you can see that the first term is totally reasonable, right? You have two things that are small, and you multiply them together. Of course, it's going to have to be small. So we're going to find delta 1 standing for first term, delta 1, not greater than 90, so that what? Absolute value of f of x minus L times the absolute value of g of x minus m is less than epsilon divided by 3 whenever absolute value of x minus a is less than delta 1. So we find a delta 1 that makes the first term less than epsilon by 3. And actually, okay, I think if I just do one little zoom out, okay, a couple little zooms out, now it fits on one line, which is really nice. So I'm gonna do that. So it fits on one line. Okay. So what is the proof? Why can we do this? So the proof of the first term, comma. Okay. This thing is small. That thing is small. So when you multiply them together, they're going to be small. So there's a million ways you could do this proof. But how about this one? Let's let delta, I'm going to call it delta f. This is the delta for f. Be chosen so that absolute value of f of x minus L is less than epsilon divided by 3. And let delta g be, okay, I'm missing the whenever. I've been spelling my whenever is wrong. Whenever. Probably you noticed that. Whenever x minus a less than delta f. So this is the delta for f. Let's make a delta for g. This is chosen so that the absolute value of g of x minus m is less than epsilon divided by 3 whenever absolute value of x minus a is less than delta g. So if both of these things are individually less than epsilon divided by 3, then what happens when we multiply them together? Then the absolute value of f of x minus L times the absolute value of g of x minus m is going to be less than epsilon divided by 3 times epsilon divided by 3. And that's because it's okay to multiply positive numbers together in inequalities, right? Everything's positive here. It's all good. Okay, so we made both of the things individually less than epsilon divided by 3. And this whole thing is epsilon divided by 3, tiny number, times epsilon divided by 3. We would like to say this is less than epsilon divided by 3. And that is true as long as epsilon divided by 3 is actually tiny and less than 1. But if it's not less than 1, then it wouldn't be true, right? If it was 2, then you square 2, you get a bigger number. So this is a little trick where we don't want just epsilon divided by 3. We want the minimum, let's do a minimum of epsilon divided by 3 and 1. And we're going to do the minimum of epsilon divided by 3 and 1. Okay. So if epsilon is actually a big number, then we shrink it down, and we make sure that each thing is individually, whichever is smaller, epsilon divided by 3 or 1. And if you do that, then this is all perfectly okay. So you end up with the minimum here of epsilon divided by 3 and 1, and the minimum of epsilon divided by 3 and 1. And now it's perfectly true. This number is whichever is smaller, epsilon divided by 3 or 1. If you multiply that by something that is less than 1, then it's definitely going to be less than epsilon divided by 3. So this holds. Okay, so for this one to hold, we need to be within delta f. For this one to hold, we need to be within delta g. Then if we set delta 1 to be the minimum of delta f and delta g, then for any x with absolute value of x minus a less than delta 1, we have this going on, and it's less than epsilon by 3. Okay, so hopefully that one makes sense, and I think, again, this is the point where this is a logically intuitive thing, right? If this is small and that is small, then when you multiply them together, it's still small. But this little lemma, it's starting to already get a little bit complicated. It might be nice to break this up into further sublemmas, but I'm going to leave it like this. Hopefully the core idea is there. Okay, so what have we done so far? We've taken what we want. We've broken it up into 3 pieces with triangle inequality. I should have written triangle inequality somewhere in words. By triangle inequality. And now we deal with the 3 terms individually. We found a delta 1, so that this guy was less than epsilon by 3. We found a delta 2, so this guy was less than epsilon by 3. And we found a delta 3, so this guy was less than epsilon by 3. And those each had their own individual proof that had nothing to do with the other proofs. So every proof is its own little thing that you can read on its own and should make sense. And actually, the proofs for 2 and 3 were the same. So we saved some, effort of the reader by having them reuse what they already read. Okay, so last but not least, it's like a one-liner to finish it off, which is we're going to say, now, let delta be the minimum of delta 1, delta 2, and delta 3. And this is really showing the reader that, look, we have 3 parts, and we want to take the smallest of those. We're making sure all 3 parts hold. Then the results of lemma 1, lemma 2, and lemma 3 all hold simultaneously whenever x minus a is less than delta. And we have, and I'm going to copy paste the main conclusion that we started with over here, which is the first and last line of the little thing we wrote. This thing is going to be less than, oh no, I lost my mouse. Okay, apparently not. Okay, well, we still have the mouse. Less than this stuff. This is less than this. And each of these 3 terms is less than epsilon divided by 3. So epsilon divided by 3 plus epsilon. Okay, why does it hate me? Epsilon divided by 3 plus epsilon divided by 3. So we have the 3 terms. Each term is bounded by epsilon by 3 by using the lemmas on the 3 terms. And this is equal to epsilon. So whenever x minus a is less than delta, this thing that we're looking for is less than epsilon. Therefore, by the definition of the limit, and if you really want, you could remind people, since epsilon was arbitrary, the limit as x goes to a of f of x times g of x equals L times m. So this difference, we make it less than epsilon, and we can do that for any epsilon. That's why the limit is L times m. And okay, that is the whole proof. So I hope you will sort of see how I took this intuition proof, things that are small, multiplying together, and going from there, how I turned that into this algebraic thing. We used triangle inequality once to split it up into 3 pieces, and then each individual piece had its own like one-liner lemma that was like one idea, one core idea in each lemma for the reader to figure out. So that is my proof of this thing. Hopefully you liked it. And otherwise, yeah, watch that black pen, red pen video is very good too. So maybe you like that proof better. Okay, bye. Okay, it's me again with one little bonus if you made it this far into the video. This type of argument that we did here, we had 3 lemmas. Each lemma proved that something was less than epsilon by 3, and then we added up the 3 things with triangle inequality. So we had 3 things that were individually small, and so summing them together was small, and we made each thing less than epsilon by 3. This is called an epsilon by 3 argument. So it's an argument that goes by making your things less than epsilon by 3 and then combining them. So that's an epsilon by 3 argument. Why am I telling you this? There's a beautiful comic that I dug up from the depths of the internet here from 2008. And I remembered this comic from when I was a student. And this is an epsilon by 3 argument. It's 3 epsilons having a fight. So I really like this comic. I thought I'd share it with you. Yeah, Brown Sharpie was this comic. It was pure genius when I was a student, and then they stopped making them. But yeah, anyway, I still have fond memories of Brown Sharpie. Okay, that was a little bonus if you made it that far into the video. Don't forget to like and subscribe.